Hello, and welcome to Astronomy 100. In our previous segment, we saw how very important it is to understand the concept of Wien's law. And if you recall, Wien's law is a way to allow us to determine the temperature of an object based on the light that that object is producing. If we can measure the light coming from the object, pass it through a prism to spread it out into its component colors, and then measure the brightness of each color, we get what's called a blackbody curve, and then that blackbody curve will tell us information about the temperature of the object. In this segment, what I want to do is show you some examples of Wien's law to help you further understand how very important this is, and of course how very useful it can become. So let's look at our first example here. Now, the example I want to give you is, first let's put up a formula. I realize there's some math on the screen here, but let me show you what this is trying to say. What if you were to try to determine the temperature, in this case, or the light that is coming from somebody like a person or an animal, somebody that's the same temperature that human body temperature is. So let me show you how this works. Here is the formula for Wien's law. This is the original version, where if you plug in the value for t into our constant here and then calculate lambda max, what this will actually do is tell us what wavelength the light coming from an object is based on the temperature of the body. So what I have done is I plugged in the value of 305, and 305 is actually the temperature of a normal healthy human. So 98 degrees Fahrenheit translated into kelvins is 305 kelvins. And it's at this point that I'll mention that for this constant to work, the temperature has to be in units on the absolute scale. So it has to be in kelvins. And refer back to the previous segment to remind yourself what that means. So if we plug in the value for human, normal, healthy, 98.6 or 305 kelvins, what we calculate is 95,081, and this A should have a little halo on it. PowerPoint's not very cooperative in this case, but that should have a halo. So this is 95,081 angstroms. Now what this means is, based on your healthy body temperature, you are glowing with light, that the greatest amount of light that you are glowing is with this wavelength, 95,000 angstroms. Now we don't see it 95,000 angstroms. This is longer than what we are capable of seeing. If you recall, red is at about 7,000 angstroms, so we don't see anything longer in wavelength than red. So this is in the infrared. How do we actually see something in the infrared? Well, we have to have a special camera that allows us to do that. And here's a photograph from just such a camera. This is the image of somebody's hand and their arm taken with an infrared camera. So this camera has the ability to see wavelengths that we can't see. So this camera can see wavelengths that are longer than the red, where we obviously have a limit to what we can see. Now to show you how this works, the camera has a computer chip that will assign random colors, or not really random, but artificial colors based on temperature. So this is the scale that shows you that the color that is associated with this 92 degrees. This is the color associated with 90 degrees. This is the color associated with 88 degrees. So this camera cannot measure any light that is associated with a temperature lower than 86.3 or anything higher than 92.3. So what this means is, if the object has a temperature that is lower than this or higher than this in this range, it will associate a color that goes with that temperature based on Wien's law. So the idea is, it can detect the light that it is getting into the camera and then attach a temperature to it that it will tell us the temperature based on color. So sometimes these are called temperature maps. Now notice that this person's hand is a variety of temperatures. You can see that he's got some warm spots. Remember that these colors are for higher temperatures. And then he's got some cool spots, maybe a little bit of circulation issues because some cold fingertips there. And then you'll notice that his palm is a little bit cool. And you'll notice right here that his hand and his arm seem to be detached. Now, in reality, they're not detached. What you are actually seeing is the watch that he has around his wrist. The watch doesn't show up because its temperature is cooler than the minimum temperature that this thing can measure. So all we can tell is that his watch is cooler than 86.3 degrees. And so what you get an idea of is how Wien's law can tell us the temperature of something based on the light that that object is producing. And so we don't have to touch any part of his hand. His hand is now telling us the variety of temperatures that it has. Kind of cool. Now let's show you a couple more examples. There's a website that NASA has produced where they took a couple of these cameras around and just went through their daily, day-to-day life and took some interesting pictures. Let me share a few with these. Now remember, light carries information about the temperature of the object. So let's start with this one here. This is just a hair dryer that's laying on a linoleum floor. And although we can't tell in this regular visible light picture, the hair dryer is turned on. So there's hot air blowing out of it. But if you take the very same scene and you photograph it with an infrared camera, you get this. And what you can clearly see is there are hot elements inside of the nose of this hair dryer, and then when the air blows past the elements, it heats the air. You can actually see that the air has a variety of different temperatures, hot in the middle and cool on the edges. So here is a hair dryer with hot air blowing out of it. Kind of cool. Now I admit this one looks a little strange, and the person who took this picture must have a pet alligator. I don't really know the background of that, but you can see in this image, this regular visible light image, is that he's holding this alligator who's quietly sitting on his lap. But one of the things that you often hear about reptiles is that they are cold-blooded. So that's why I chose this picture. Now watch what happens when we take an image of this alligator in the infrared. Notice how the temperature of the alligator is quite cool compared to the temperature of the man who is holding this alligator. So good thing that the alligator is cold-blooded, because when they're kind of cold, they're very inactive, and that's probably the reason why he feels it's safe to hold this alligator on his lap. Here was an interesting one. It's just an ordinary ice cube sitting in a tray. But the reason why I chose this one is because ice cubes are obviously very cold, and then the tray is going to be much warmer. So we're going to have a big difference in temperature from the cold ice cube to the warmer tray. Now look at the image in the infrared. So you can clearly see very cold ice, and then the water that it's sitting in is a little bit warmer until we get to the tray itself, which is obviously quite warm, and the table it's sitting on. It's kind of cool. Now, your eyes are not deceiving you. You are actually seeing two burritos sitting on, I guess, a table in this picture. But these are burritos that have come out of the microwave. And if you've ever heated up burritos in a microwave oven, one of the things that you quickly realize is that the microwave oven is not very good at heating things. You can see with this burrito, still very, very hot right here, but of course very cold right here. And anytime you bite into a microwave burrito, part of it is burning the roof of your mouth, and then the very next bite is very cold. So you can actually see that these burritos are not evenly heated up. Now this last one I want to show you looks a little strange, but there's a very good reason, and this is really the most important of all the 5 pictures. What you have here is a man who he's holding his arm inside of an ordinary garden trash bag. So these are those green trash bags that you would use in your backyard. The purpose of this picture is to show you that you can't see anything through the trash bag. He's clearly holding up his arm and his hand, but visible light will not pass through the trash bag. It blocks visible light. But what we know is the trash bag is transparent to infrared light. So the infrared light coming from his arm and his hand based on his body temperature, that infrared light is able to pass through the trash bag, and it's as if the trash bag isn't even there. So the point is sometimes by switching to a different wavelength, we can see through something that might otherwise block our view. Kind of cool. Now let's do something more related to astronomy. Let me show you a few examples here. This is an image of Jupiter. This is an image of Jupiter seen with visible light. In other words, if you were to look at it with your own eyes through a telescope, and all the features that we're familiar with Jupiter. So this is Jupiter in visible light. Now remember that Jupiter is reflecting sunlight. That's the reason why we can see it. So this is all the sunlight reflecting off of the cloud tops of Jupiter. But watch what happens when we look at Jupiter in the infrared. So when using an infrared camera, what we can now see is that Jupiter shows us light coming from different parts of it, because now the light that you see coming from Jupiter is actually the light that Jupiter is making. So Jupiter is much hotter in its interior than it is on the cloud surfaces. Notice how the surfaces of the clouds are rather dark in the infrared, but the interior of Jupiter is actually quite bright in the infrared, which tells us Jupiter is hotter on the inside than it is on the outside. And notice that we don't even have to go to Jupiter to figure that out. The light is telling us that information. And then lastly, here's a photograph of Jupiter, but taken with an X-ray camera. So the ability to determine X-ray light coming from an object recorded in a way that we don't normally see with our eyes. Now think for a moment. Wien's law says that the hotter the object, the shorter the wavelength is that it's going to produce. So if you are seeing X-ray light, this is coming from places that are extraordinarily high in temperature or some other source of X-ray. So X-ray light is towards the shortest end of the electromagnetic spectrum. It's going to be very hot objects, and radio light comes from the long end of the electromagnetic spectrum, be very cool objects. A couple of final examples. Here is the surface of the sun, and this is an image of the surface of the sun that is taken with visible light. It happens to be a black and white picture. The temperature, excuse me, of the surface of the sun is about 6,000 kelvins, and this is what you would normally see with your eyes. Now, if we switch to an ultraviolet camera, what you'll notice is that in the ultraviolet, all of those parts of the sun become dark because these parts of the surface of the sun are not this temperature. So this is a camera that's going to show us all of the places on the sun that are 20,000 kelvins, but these places on the sun are only 6,000 kelvins. So they appear dark, but the places that are very hot obviously appear much brighter. Now let's go to the far ultraviolet, and what we notice is that going to a shorter wavelength, we end up going to also places that are much higher in temperature. Remember Wien's law, shorter wavelength, higher temperature. So far into the ultraviolet, what we end up with is most of the parts of the surface of the sun are quite dark because they're not 150,000 kelvins, but they're also very, very cool in temperature. But notice how there are a few places around the sun that are extraordinarily hot. These are places that we would normally never know about unless we were to look at the sun with an ultraviolet camera. So you can see much more information about the sun based on the temperature of different places on the sun and the regions that produce those temperatures. Now lastly, I want to show you a couple of images that are just related to that image I showed you of the guy holding up the trash bag. In this case, what you'll notice is we have a cloud in space. This particular cloud is called the Eagle Nebula, and you'll notice that it has the shape that is a little reminiscent of an eagle. That's where it gets its nickname. Now inside of this cloud, there are many, many things embedded in the cloud that we can't see with our eyes when we look at it with visible light. But notice what happens when we switch to an infrared image of the very same cloud. We get an enormous amount of information. We get to see many, many more stars, star-forming region, all the details about this cloud that we otherwise wouldn't have seen. So in other words, by switching to the infrared, we can see through the dust, as if we're looking through the trash bag that the man had surrounding his hand. We have the ability to see through dust by switching to the infrared. So by using Wien's law as a concept, and by exploring our universe in different wavelengths, we can understand and learn things about objects in our universe that we otherwise wouldn't have known if we were just relying on the light that we can see with our eyes. So Wien's law tells us the temperature of an object based on the light that it's producing, but Wien's law also tells us that there are ways to see more information about an object based on looking at it with different wavelengths. So it's a very powerful tool. We're just about out of time. I hope you'll join me again next time.